Hi, Mr. Corsi here. This video has the complete detailed solutions to all the questions in the AQA higher tier GCSE Mathematics Paper 1 exam from 2024. Now there's a lot of questions, but to find the particular question you might be interested in, you just need to scroll along the timeline below the video. So I hope you find these solutions are useful in your journey towards success in your GCSE exam. So here we have question 1, and we're asked to work out 12 squared and then divide it by the result of finding a third of the square root of 36. So let's tackle the 12 squared first. That means 12 times 12. Some people just know that's 144. A lot of people have to work that out. Remember, there's no calculator in this paper. One of the methods that you might have been taught, 2 times 2 is 4, 2 times 1 is 2. Now we're in the tens column, so let's just put a 0 there so that we don't put them in the wrong place. So really we're doing 10 times a 2 being 20, and 1 times 1 is 1. 10 times a 10 is 100. And then we add up. And that's 4 and that's 1. So there's the 144. Other people do it like this. They say 12 is 10 and a 2. The other 12 is a 10 and a 2. And we'll put it into a table of results so that we've got a place for all the different multiplications. 10 times 10 is 100. 10 times 2 is 20. 2 times 10 is 20. And 2 times 2 is 4. So I've got 100. 20 and 20 is 40. 4. 144. So again, that's the same result as there. So that's the first calculation. Now let's tackle what's in the bracket. First of all, square root of 36. Now the square root means a number times itself gives you 36. 6 sixes are 36. So that's what the square root of 36 is. 1/3 of that we have to divide 6 by 3. Well, 3 goes into 6 twice. So in the brackets we've got a 2. And we've now got to divide 144 by 2. So 2 into that 14 would go 7. 2 into that 4 goes 2. So we end up with the answer of 72, and not a calculator in sight. Well, here we are with question 2, and we're asked to measure the shortest distance from this point P to that line, and we have to give our answer in millimetres. So let's get a full-scale drawing of this, and let's introduce a ruler. And maybe we should just line it up and say it's around about 40 millimetres, 4 centimetres. However, you think about it, we could make a different angle. Suppose we make it that angle, then line it up. Look, it's gone down to about 34 millimetres. We've got a shorter distance. Now, what we should be doing is lining up this ruler so that it's perpendicular to this line. That would give us the shortest distance from the point P to the line. So I'll now rotate the ruler so that it looks as best we can see that it forms a right angle with that line. And I think that's pretty good. Now, is that how we measure? No, it's not. We start from the first mark on the ruler down to that point. So there's my ruler lined up for the measurement. And if we look at that, we would see that it's around 32 millimeters. 32 to 33 millimeters would probably give you the, well, it will give you the full marks. So for my measurement, I'm going to say 32 millimeters. Here we have question 3, and we're told that this vector, -3, 7, translates A to B. We're asked to write down the vector that translates B back to A. So it's the vector that undoes what this vector has just done. Well, to explain what's going on, let's have a look at a grid. And we start off at a point A, and let's follow the instructions of this vector. The x component, that's the first number here, is -3. Now the x component tells us how far to the left or the right to go. So in this case it's negative, so we'd go to the left 3 squares. The second number, 7, that's the up and down number, and it's positive, so we would move 7 squares up. 1, 2, 3, 4, 5, 6, 7. So there's what the vector does to the point A. It moves it up to the point B. Now, we're looking for the vector that moves B back down to A. Well, let's just count squares. We would have to move 3 to the right. That's +3 for the x component, and then 7 squares down, that's -7 for the y component. So to get from B to A, 3 along, 7 down. And you'll notice that they're the negatives of the components we started with. The x component was -3, it's now the negative of -3, it's +3, and the y component 7, and it's now the negative of that. So here we have question 4, and we're told that the attendance for a rugby match is 8,400, and that number's been rounded to the nearest 100, and we're asked to write down the minimum possible attendance. Well, it would be useful if we put that number on a number line. So this is a number line, and we've got 84 hundreds. So this mark here would be 83 hundredths, and this would be 85 hundredths. And we're asked what the least value of this, because it's a rounded number. Now, halfway between 8,300 and 8,400 would be 8,350. Now let's think what we would do if we take 8,350 and round it to the nearest 100. Well, there's the thousands, there's the hundreds, would be chopping a 5 off. Now the rule is, if you chop a 5 off, that number 3 would go up 1. So we would be producing 8400 to the nearest 100, 8400. So it would round up to 8,400 according to the rules. So anything below that, suppose we had 8,349 for the attendance. When you round that off to the nearest 100, you're chopping a 4 off. That 3 would stay as a 3, and you'd get 8,300. So according to the rule that chopping a 5 off, that 3 goes up, then the least possible value is 8,350. Now in part 2 of this question we're asked similarly to write down the maximum possible attendance. So halfway between 8,400 and 8,500 would be 8,450. That's 8,450. Now you would imagine that that would be the maximum value that we could use. However, think what happens if we round off 8,450 to the nearest 100. We'd be chopping a 5 off, so that 4 would move up to 8,500. So this number belongs there. So we would have to go one smaller. Now remember, these are whole numbers we're using because we're talking about attendance at a rugby match. It's not a continuous variable, as they say, it's a discrete variable. They're just whole numbers. So we would have to go one below 8,450, and that would be 8,449. And if we'd asked to round this to the nearest 100, we definitely would be keeping that 4, and it would go to 8,400, which is what we were told was the attendance at this rugby match. So the greatest value, the maximum possible attendance, would not be 8,450, because that would go rounding up. It would be 8,449. 8,449. So here we have question 5, and we're told that in a school year there are 78 students, and we're told various facts about them, wearing glasses and being left-handed. And we're asked in this part A of the question to complete this Venn diagram. Now, inside this circle labelled G, we've got all the students who wear glasses, and we're told there are 28 of them. 28 wear glasses. However, there are two types. Those that are left-handed and those that aren't. So we've to decide how many of the students that wear glasses are left-handed, and we can do that by calculating a quarter of the 28. We're told a quarter of the ones who wear glasses are left-handed. Now, a quarter of 28, 4 into 28, 4 sevens are 28, so 7 are left-handed. So we know now that 7 of the students that wear glasses are left-handed. The rest of them would be what? 28, and take away these 7, well, they would be right-handed. So the 21 plus the 7 make up the 28 who wear glasses. So far so good. Next fact that we haven't used, 30% of the students who do not wear glasses are left-handed. Now if you take all the students, there's 78 of them. All students, there's 78 of them. Some of them wear glasses, 28 we know, and the rest don't wear glasses. Now how do we find out how many don't wear glasses? We take 28 away from 78, that would give us 50. If you like, you can set up your subtraction and do that. You'll get it 50. So we know 50 don't wear glasses. 30% of them are left-handed. Now that'll be this number in here, left-handed but outside the glasses circle. So they don't wear glasses but they're left-handed. So we've now to work out 30% of 50. Well, let's figure that out. 30% means divide by 100 of, we just replace it by times. So it's 30 over 100 times 50. Now we can do a lot of cancelling here, top and bottom numbers. 50 goes into 50 once, 50 into 100 goes twice. So we've got 30 over 2, a half of 30, that's 15. So 15 students left-handed do not wear glasses. The total so far is 21 and 7 and 15. Now if we add up all of these, you should end up with 43. Again, set up your little addition. No calculator in this paper, and you'll get your 43 from that. So we have 43, the rest equals, well, remember we had 78 students altogether and we've accounted for 43 of them. That leaves 35. Set up your subtraction. No calculators. So the rest of these students, the ones that are not left-handed and don't wear glasses, so the right-handed non-glass wearers, 35 of them. Okay, that's that complete. Let's move on to part B. And in part B, we're told that a left-handed student is chosen at random. Work out the probability that he wears or she wears glasses. So the left, let's look at the left-handed ones. There they are. And we're told that one of these is chosen at random. Now there's 22 left-handed students. (22) altogether, that's 7 plus 15 inside this circle. One of these is chosen at random. What's the probability that that student wears glasses? Well, there's only 7 out of these 22 that wear glasses. So 7 out of 22. And we would therefore write 7 over 22. That's the probability, 7 out of 22, 7 22nds. That's the probability that a student chosen at random that's left-handed will be wearing glasses. So here we have question 6, and we're given a table showing the number of workers at a company in different years. We go from 2015 all the way up to 2022. And they've started plotting a time series graph representing this data, and they've so far got 4 points in there. It's the first 4 entries in this table. So they've put in the entries from 2015 up to 2018. And in part A, we're asked to complete that graph. So let's look at a larger diagram, which will make it a bit easier for us. And let's just check this last entry that they've put in. In 2018 there were 52 workers. So we're along with a heavy line there. Each heavy line along the graph there represents a new year. So this heavy line here, 2018. And you'll notice that the heavy line that goes along to 50 workers, the next heavy line up there goes along to 60 workers. So there's 10 workers represented by 1, 2, 3, 4, 5 little squares. So each little square will represent 2 workers. So that's why this cross is 1 square up from the 50 line. It represents 52, which is what the entry for 2018 is. So let's go ahead and try and complete this graph. We'll put in the crosses first and then join them up afterwards with straight lines. So 2019, 62. So 2019, there's the 60 line I'm at. 1 square above that. There we are. And then 2020, 70. There's the 70 line there. (2021) 76. So that's 72, 4, 6. That's 3 squares up from the 70 line. And then final entry will be 2022. That's 80 workers. So there's 2022 line, and there, that heavy line there is the one representing 80 workers. So I've now got my crosses on there, and I'll use a ruler to join them up neatly with straight line. Now you can see as I go from year to year that the increase in workers is getting slightly less year by year. We'll maybe need to think about that when we're estimating future trends. So there's my completion of the graph. Next, let's have a look at part B. It says estimate the number of workers at the company in 2023. So the workers are increasing faster here, they're increasing less up here. So I would probably use the latest trend as a good estimate. Let's increase it ever so slightly. So we'll do this in red so we don't get confused with the previous ones. And with that method of estimating, I'm producing an estimate of 80 with 2 squares above 80. That would be 84. So my estimate for the 2023 figures is 84. Now there are different ways of doing that. Some people might take the general trend. This is a rough estimate line here, which would put the estimate slightly higher. But I think from 82 up to about 88, anything between there would give you a mark. So here's question 7, and we're given a cone. We're told the radius is 5, that this perpendicular height is 12, and this slant height is 13. Now these words that I used are going to be important. This is the slant height. This is the perpendicular height. And of course this is the radius. Now the base of that cone is a circle. We're looking at it in a representation of 3 dimensions, so it looks a bit squashed, but if that base is a perfect circle. Now we're told the curved surface area of a cone is given by this formula: pi times the radius times the slant height, which is called L. Pi times r times L. That's the radius. That's the slant height. That, remember, we said was the perpendicular height. And Beth's trying to work out the curved surface area in terms of pi. So here's her working. She's got pi times 5 times 12. She's used pi times 5 times 12. And she gets 60 pi. 5 times 12 is 60. So she's got the right answer from using these numbers. What mistake has she made? Well, has she got the radius right? Yes, she has. Has she got the slant height right? No, she hasn't. The slant height is 13, not 12. She's taken the perpendicular height instead of the slant height. So we'd have to say that she used the perpendicular height, and that's 12, instead of the slant height. Of 13. So she did make a mistake. Let's have a look at part B. Adam uses pi equals 3 to estimate the area of the base of the cone. And we have to work out his estimate. Now, remember I said the base of this cone is a circle. And the formula for the area of a circle is given by pi r squared. That just means pi times r times r. That is the area of a circle formula. So his estimate is 3, that's what he's using for pi, approximately 3, times the radius was 5, times another 5. Now there are all sorts of ways of doing that. 5 5s are 25. 3 lots of 25 is 75. Another way of doing it, 3 5s are 15. 15 times 5, you could do the remultiplications if you need. 5 5s 25, 2 to carry, 5 1s are 5, plus 2, 7. So 75, whether it's 3 lots of 25 or 15 lots of 5. So the answer, 75 square centimetres. Now there is a part C in this question. Beth's recovered from her mistake. She's now using 3.14 to estimate the area of the base. And we're asked, is her estimate going to be more or less than that estimate that Adam has used? Well, let's look at what's going on. She uses 3.14 times 5 times 5. So she's multiplying these three numbers together. Adam was multiplying these three numbers together. Now you'll notice she's using a larger estimate for pi than Adam was. Beth's estimate for pi, that's 3.14, is larger than Adam's. So therefore Beth's estimate will be larger than Adam's estimate. So we're going to have more than box is going to be ticked for that one. There we go. So here we have question 8, and we're asked to solve this equation. 7x minus 22 is equal to 4x plus 29. Now the wonderful thing about an equation is that the left-hand side of the equal sign and the right-hand side of the equal sign are balanced. You can think of a balance where whatever's there must be exactly the same as what's there. So if I do something or take away something or add something to the left-hand side, I must do exactly the same to the right-hand side, otherwise it will not be balanced. And the general aim is to get letters on the left and numbers on the right. So keep that in mind. So we'll look at this and say, well, okay, we've got letters. There's 7 lots of x on the left. This number is not in the right place. Let's add 22. Now, why am I adding 22? Well, it's the opposite of taking away 22. Take away 22, add 22, that vanishes. So I'll be adding 22 to this side. Well, let's not do too much at once. Let's just do that. We've not touched this 7x. We've added 22 to this, so that negative 22 disappears. There's your equal sign. We've now got 4x there, and we're adding 22 to 29. Now that'll be 51. If you're not sure of that, set up your addition. 9 and 2 is 11. 2 and 2 is 4 and 1's 5. So there's your 51. Remember, no calculators in this paper. So we've moved forward. 4x is on the right. We're supposed to get numbers on the right, letters on the left. So that 4x should disappear. We'll take away 4x. Now, what did I say? If we do something to the right-hand side of that equation, we must do exactly the same to the left, or we can't write an equal sign there. They're not equal. So taking 4x from the right, I'll take 4x from the left. So what does that give us? Well, 7 lots of x, and take away 4 of them, we'll have 3 lots of x. And that equals, now we've taken away these 4x, we'll have no x's left on the right hand side, but we'll have a 51. So what's next? Well, we really want 1x, we don't want 3 lots of x. So what's the opposite of multiplying by 3? Well, that's dividing by 3. So if I divide this by 3, I'll end up with that 3 disappearing, and I'll get 1x. And remember, divide 3 on the left, I have to divide 3 on the right to keep the thing balanced. So let's work that out. As we said, a third of 3x, or 3x divided by 3, will be 1x. We just write that as x. And 51 divided by 3, 3 into 5 goes 1 with 2. 3 into 21 is 7. So we've got 17. That's a third of 51. So we've solved it. That's the value of x. So here we have question 9. And we're told that in a house the floor area of the living room is 26 square metres and the floor area of the kitchen is smaller, it's 16.4 square metres. And we have to express the area of the living room as a fraction of the area of the kitchen, giving our answer in simplest form. I think what we should start with is a simpler example. Let's take these two rectangles and let's suppose that this one has an area of 10 square centimetres and that this one has an area of 5 square centimetres. We'll call this rectangle 1 and we'll call this one rectangle 2. Now just looking at this, you'd immediately say, well, look, the area of rectangle 2 is a half the area of rectangle 1. So express the area of rectangle 2 as a fraction of the area of rectangle 1. That would be 1/2. We've got 5 over 10. Rectangle 2 compared to rectangle 1. Rectangle 2 compared to rectangle 1. 5 over 10. 1/2. That rectangle is 1/2 the area of this rectangle. Now if we have to do it the other way around, we would say that rectangle 1 compared to rectangle 2 has twice the area, and that would be 10 over 5. We've got rectangle 1 this time compared to rectangle 2. Now we know that that area is twice that. 10 over 5, 5 into 10 goes twice. So this is the number 2, this is the number 1/2. So the one you're comparing with the other one, that goes on top. So in this case, the area of living room compared to the area of the kitchen, the living room would go on the top, the kitchen would go on the bottom of the fraction. So if we've got this being the living room, which is 26 square metres, and we've got this being the kitchen as 16.4 square metres, let's write that down. Living room, kitchen, and this time we have to express the area of the living room compared to the area of the kitchen. So it's certainly a bigger fraction than 1, and we look at these rectangles up there, we got an answer of 2 when we compared the area of rectangle 1 with the area of rectangle 2. It was twice the size. The fraction was 10 over 5. So it's not the case that the smallest number always has to be on the top. You look very carefully at the order that they're telling you to use these. So it's the area of the living room compared to the area of the kitchen. Living room on top and kitchen on the bottom. So what is 26 over 16.4? Well, there's a decimal point in there which is annoying. So let's multiply top and bottom of this fraction by 10. Remember, you're allowed to multiply the top and the bottom of a fraction by the same number. Now, the reason we would do that is to get rid of that decimal point. So on the top of the fraction we've got 260. On the bottom of the fraction, that decimal point will move 1 to the right, or alternatively the digits would move 1 column to the left. Very much depends how you're thinking about it, or how you've been taught to think about it. So there's the fraction with that decimal point removed. Now the question asks us to give our answer in its simplest form. So we'll need to cancel this fraction down if at all possible. Now these numbers are both even, so we divide both of them by 2, and a half of 200 is 100, a half of 60 would be 30, so there's 130 on the top, and a half of that 16 would be the 8, half of 160 is 80, and a half of the 4 is 2. Both even still, so let's keep going. A half of 130, now there's no calculators in this paper, so 2 into 13, 2 6s are 12, 2 into 10 goes 5, so we get 65 over, and then a half of 82, a half of 80 would be 40, a half of the 2 is 1. So it's 65 over 41, and this fellow at the bottom, this 41, is a prime number. There are no other factors in that other than 1 and itself 41. So there are no more cancelling down. So 65 over 41 would be perfectly acceptable as an answer in this question. That's the fraction. So here we have question 10. And in part A, we've got this inequality, a statement here about numbers. And it says that the numbers have to lie between -2 and 4. And we have to show this on that number line. Well, here's a larger version of the number line. The inequality we're looking at, -2 is less than all the numbers, and all the numbers are less than 4. So they're jammed between -2 and 4. Now, these are strictly less than signs. They're not less than or equal to. So we're not allowed -2 and we're not allowed 4. So at the lower end, we go down to -2, but we're not allowed it. That's shown by an empty circle. It stops. They stop up at 4, but we're not allowed 4. So again, an empty circle goes there. And we have to indicate that all the numbers on this number line in between -2 and 4 are the ones that we're after. So let's get a ruler onto this. And we can now draw a line between these two empty circles. So there it is, the number line indicating that we want all the numbers between -2 and 4, but we do not include -2 and we do not include 4. So that's part A. Let's move on to part B, and we're given an inequality to solve this time. So it says 5y plus 14 is greater than or equal to 11. Now we treat this as we would an equation, and remember, if we're saying that this side is greater than or equal to this side, anything we do to this side would have to be done to the other side. Otherwise the inequality would not be true. So remember, the general aim here is to get letters on the left of that inequality sign and numbers should be on the right. So we can immediately see that this plus 14 is on the wrong side of that inequality sign. So what's the opposite of adding 14? Well, it's taking away 14. So we'll take away 14 from both sides, and then that inequality will still be true. Must do the same to both sides, as we did for equations, solving equations. We do the same to both sides. So we haven't touched the 5y. We've got rid of that 14, and that's still greater than or equal to, now 11 take away 14 would be negative 3. Now what's next? Well, to get rid of this times 5, we do the opposite, which would be divide by 5. And if we do that on the left hand side, we must do that on the right hand side. So 1/5 of 5y, that would be 1y. We've cancelled, we've got rid of that 5. So y would be greater than or equal to, now we've got negative 3 divided by 5. And what is that answer? Well, a negative divided by a positive gives you a negative number. And 3 divided by 5 is written as 3/5. So don't leave it as negative 3 divided by 5. It's the negative of 3/5. That's your final answer. So all the numbers greater than or equal to negative 3/5. So here we have question 11, and we're given a diagram with a couple of shapes, and we have to describe fully the single transformation that maps shape A, that's the larger shape, onto the smaller shape. So the word they're looking for here is enlargement. And for an enlargement, you need two things. You need to know a scale factor. That measures how much bigger or how much smaller the new figure is, the new shape is, compared to the old one. And also, we need a centre. Now let's tackle the scale factor first. So we're going from this large shape, A, to a smaller shape, B. Let's look at the lengths of the lines on the sides. This bottom edge of shape A is 4 units long, 4 squares. Let's look at the corresponding bottom edge of shape B. It's only 2 squares long. So we've gone from 4 to 2. That's a half. We've taken this side and halved it to get this side. So we'd say that the scale factor is 1/2. The small shape is a half of the larger shape when it comes to the lengths of all the sides, and that's how you'd work out the scale factor. Now the centre. Let's have a look and see if we can find the centre. And the way we do this is to look at a point on the larger shape and look for the corresponding point on the smaller shape and then join them up. So you would take your ruler and line your ruler up so that it passes through both of these points. There it is. And we draw that line in. Now we do the same again for another pair of points. So this corner of the shape A corresponds to this corner of shape B. So again, we'll take the ruler and see if we can fit it exactly to these. You've got to be very careful with your setting up here. Now I'm getting that. That's pretty good. Let's join them up. And you'll notice what's happened, that these two lines have met down at this point. Let's take another pair of points just to confirm that. This corner or vertex of shape A corresponds to this vertex of shape B. Now that's an easier one to see where the line in this case goes, because it's a vertical line. It passes through these 2 points parallel to the y-axis. So all points and their corresponding point in the smaller shape seem to pass through this point. And this is the point negative, or 1, negative 7. And that's called the centre of this enlargement. Now, even though it's been reduced in size, we still call it an enlargement, because the scale factor of a half will then tell you that the size of the shape is going to be reduced. If the enlargement scale factor was greater than 1, say 2 for instance, then the corresponding shape would be twice the size. And it really would look like what you think of as an enlargement. So the scale factor is 1/2, and the centre of that enlargement is 1, negative 7. So in your working you would say that it's an enlargement, that its scale factor is 1/2, that the centre is 1, negative 7, and that would give you your 3 marks. Now here's a little demonstration of how things change in a diagram like this when we change the scale factor. At present, this is the picture you had in the question. Your scale factor is 1/2. Let's increase that scale factor. And you can see what happens. When the scale factor is 1, the shape is unchanged. When the scale factor goes larger than 1, for instance, suppose we end up at 2 for the scale factor, then you'll notice that this lower edge, which had a length 4, has now got a length of 8. That's twice the size that we started with. So that's a demonstration of how this transformation, this enlargement, affects the shape B from the shape A. And there it just disappears. When the scale factor is 0, it's vanished into the centre. So there's the picture as it was given to us. The other thing we can do is to see how, when we move the centre around, what happens to this reduced image. Well, there you go. You can see that it's always, if you like, halfway between the point and the centre. The corresponding point in the small shape is always halfway between the centre and the other point. So let's put it back where it started. And now here's the picture with the lines that we drew in that all met at the centre. And if we move that centre around now, you can see how these lines from a point in the larger shape to the corresponding shape in the smaller shape always meet at the centre. And that's also true if we increase the scale of that enlargement. So I hope that's given you a better feeling for how an enlargement works. So here we have question 12, and we're shown this diagram of a sector of a circle which has a radius of 12 and there's an angle of 60 degrees there. And we've to work out the length of this arc, giving our answer in terms of pi. So let's have a look at a larger diagram. There it is. And I think it would help if we imagined a complete circle. And you'll notice that this arc that we're asked to calculate is part of a complete circumference of a circle. So we have 60 degrees at the centre of this circle. And we're asked to work out the length of this arc. Well, let's look at a little animation first. So let's increase the angle at the centre. So as the angle at the centre increases, so does the arc length. There we're approaching a semicircle, half of the circumference, 180 at the centre. There's about 3/4 of the circumference. And then we're approaching an angle at the centre of 360 degrees. That's the complete circumference of the circle. So let's wind that back and let's stop at 180 degrees at the centre. Now that's 180 degrees compared to 360. 180 over 360 is 1/2, so we're getting a half of the circumference of the circle. Now let's stop off at 90 degrees. 90 over 360 is 1/4, and we're getting 1/4 of the circumference of the circle. 90 compared to 360. And there we've got 0 degrees at the centre. So let's get back to the angle that we started with, 60 degrees. So the length of the arc that we're looking for will be 60 compared to 360, that fraction of the circumference. Now, 60 over 360 can cancel by 10. 6 into 6 goes 1. 6 into 36 goes 6. That's 1/6 of the circumference. Now, do we know what the circumference is? Well, yes, we do. There's a formula that tells us the circumference of a circle is 2 times pi times the radius. 2 times pi, in this case, times 12. So that's 24 pi. So it's 1/6 of 24 times pi. And 6 goes into 24 4 times. 1/6 of 24 is 4. So this arc length is 4 pi centimetres. Well, here we have question 13, and we're told that A, B, C, D, E is a pentagon with AB, there's one of the sides, length 7 centimetres. Now 1, 2, 3, 4, 5, 6, 7. Okay, so this is a square centimetre grid. That line AB is 7 centimetres long. Each little square is 1 centimetre squared. So let's look at the information they're given. We have to complete the labelled drawing of this pentagon. So we're told that BC is 6 centimetres and that AB and BC are perpendicular. Now that means they're at right angles to each other. So B to C must form a right angle. So C must be along this line, and it's 6 centimetres long from B to C. So 1, 2, 3, 4, 5, 6. So that must be the point C. So let's get the ruler into this, and we'll draw a nice line, straight line between B and C. So far so good. So we've used this information and we've used this information. Now we're now told that AB and DC are equal and parallel. Now there's AB, so DC parallel, going in the same direction and equal length. DC would be from there to there. Same length as AB and in the same direction as AB. So we'll get the ruler into this and draw a nice straight line. Between C and D. So far so good. That's the third piece of information used up. Now we're told that the area of the pentagon is 54 square centimetres and that it has exactly one line of symmetry. Now I can see a left hand and a right hand of this. I can see where the line of symmetry is going to go. It would have to be right down the middle of this diagram. So let's draw that. It's usual to draw lines of symmetry with a dotted line. So that's the line of symmetry. So whatever goes on the left hand half will mirror what goes on the right hand half. And we're told the area of the pentagon is 54 square centimetres. Now I can see a rectangle here which has an area of 6 times 7. Now 6 times 7 is 42. So if that was just a rectangle, ABCD would have an area of 42, but we're told the pentagon, there's another 2 sides to add, has an area of 54. Now 54 minus 42 gives us 12 square centimetres. So we have to add 2 more sides, and remember this is an axis of symmetry, so there's a triangle, an isosceles triangle going to be built on the top of this, and the area of that triangle is going to be 12 square centimetres. Now, remember, areas of triangles be a half the base times the height, and that's supposed to be 12. A half the base times the height is going to be 12. And we can see that the base of this triangle is 6 centimetres long. So it's a half of 6 times the height. Now we should be able to work out the height from that. A half of 6 is 3. So 3 times the height is 12. Well, 3 fours are 12. So the height would be 4 centimetres. And that's going to be, there's the base AD. The height is 1, 2, 3, 4 centimetres. A, B, C, D, E. And we must join this up using the ruler again. So there's one side. And there's the fifth side. So this is a pentagon, and we've taken account of all the pieces of information that are given. It's labelled, all the points, all the vertices of this pentagon, all 5 of them are labelled according to this name A, B, C, D, E. So here's question 14, and we're given information about the cost of chocolate bars and mints, packets of mints. We're told 4 chocolate bars and 3 packets of mints cost £4.70, 5 chocolate bars and 1 packet of mints cost £4.50. We've to work out what the chocolate bars and the mints, the packets of mints, cost. So the first thing is to put variables in, that's letters for the prices. So if we say a choc bar costs C pence. Let's work in pence so that we don't have decimal points. And mints cost M pence. So our first task is to get this information that we're given in terms of C and M, these 2 costs that we're trying to find out. So 4 chocolate bars would therefore cost 4 lots of C pence, and 3 packets of mints would cost 3 lots of M. And we're told that total comes to £4.70. That's 470 pence. So that's the first piece of information written as an equation using these 2 variables which we're using for the unknown costs. Second piece of information, 5 chocolate bars. Well, what do 5 chocolate bars cost? They cost 5 times C. And 1 packet of mints, that's just M pence. And we're told what that comes to. It comes to £4.50. So that's 450. So there we have 2 equations, 2 unknowns, C and M, simultaneous equations. Now, the way of solving these is to try and get the same numbers of C or the same numbers of M in each of these equations. Now, the easiest way to do that would be to multiply the second equation by 3. instead of ordering 5 chalk bars and 1 packet of mints, we would order 3 lots of that. So we'd have 15 chalk bars and 3 packets of mints. And then we can be sure that the packets of mints are the same. And you'll see why that's important in a minute. So we'll keep the first equation untouched. 4c plus 3m is 470. But if we treble our order for the second equation, so multiply by 3, instead of 5 chalk bars, we're going to get 15 chalk bars. Instead of 1 packet of mints, we'll get 3 packets of mints. And of course, that'll cost 3 times 450. Now, let's work out 3 times 450. No calculators in this paper. 3 times 0 is 0. 3 times 5 is 15, 1 to carry. 3 fours are 12, plus that 1 is 13. So that's 1350. So there we go. And let's call this equation A and this equation B. Now, to avoid negatives, let's take away the first equation from the second equation. So we're doing equation B minus equation A. So we're taking the top one away from the bottom one. So we're taking 4 chalk bars away from 15 chalk bars. That'll just leave us with 11 chalk bars. And 3 packets of mints, take away 3 packets of mints, well, they've all disappeared. And we have to do 1,350 minus 470. So 1,350 minus 470. So there's a good going subtraction for you. 0 from 0 is 0. 7 from 5. Let's take this and change it to 10 of these. So 7 from 15, that would be 8. 4 from 2, let's take one of these and make that 12. 4 from 12 is 8. So we get 880. Now, a little equation. We want rid of 11 times c. So let's do the same to both sides. We'll divide both sides by 11. Remember, you have to do the same to both sides, otherwise it won't be balanced. So we're dividing this by 11. That 11 disappears. You get 1c. And 11 into 880. Well, 11 into 88 goes 8. 8 times 11 is 88. And there's a 0. So that would be 80. Well, now that we know the value of c, let's use this first equation. Second equation, 5c plus m equals 450. Instead of having to write c, we now know that c is 80. So that becomes 5 times 80 instead of 5 times c, plus m equals 450. Now, what is 5 times 80? So 5 times 0 is 0, 5 eighths are 40. So that's 400. So 400 plus m is equal to 450. So a nice little equation. Let's get rid of this 400 by subtracting 400 from both sides. And what does that give us? Well, that 400 disappears. We get m on its own. 400 from 450 gives us 50. Now, believe it or not, we have solved this problem. It says, work out the cost of a chocolate bar. Well, C, we're saying a chocolate bar costs C pence. C is 80. A chocolate bar costs 80 pence. So a choc bar costs 80 pence. M equals 50. Mints cost 50 pence. So a packet of mints costs 50 pence. 80 and 50. So here we have question 15, and in part A we're asked between which two consecutive integers does the square root of 210 lie. Now, square numbers and square roots are intimately connected, and you should maybe know the first few square numbers, like 12 squared, that's 144. 13 squared, if you don't know these, you need to multiply them out to find out. 13 times 13, that's 169. 14 squared, swap the last two digits round, 196. And then 15 squared, 225. Now, if we look at what we're asked about the square root of 210. Now, 210 is between these two numbers, 196 and 225. Now, the other way of therefore writing all of these results, square root of 144 is 12, the square root of 169 is 13, the square root of 196 is 14, and the square root of 225 is 15. So you think about a number line, and we're looking at the square root of 196, which is 14, and we're looking at the square root of 225, which is 15, then the square root of 210 will be somewhere in between these two values, and it will be somewhere in between 14 and 15. So these are the two consecutive integers that they're asking about. The square root of 210 lies between 14 and 15. Well, okay, let's look at part B. And we're given two calculations. Calculation A is 1.92 to the power 7, and then we have to add 6.9 cubed. And in calculation B, now remember there's no calculator in this paper, so in calculation B is 5 times, and that's a cube root. That's a number times itself 3 times. It gives you 1,350,000. So these are the two calculations that were given, and we're asked to use approximations to show that this answer A, whatever it is going to be less than answer B. So let's do some approximations. 1.92 is pretty close to 2. 6.9 is pretty close to 7. Now, both these approximations I've made are bigger than the original one, so the original calculation will be less than this answer that I'm going to get. Now, let's have a look at 2 to the power 7. That's 7 2's all multiplied together. 2 times 2 is 4, times another 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64, times another 2 is 128. So that comes to 128. Now let's deal with the 7 times 7 times 7. 3 7s multiplied together. Now 7 times 7 is 49. And why don't I approximate that with 50? And again, that's a bigger approximation than originally. It's close to 50. And 5 7s are 35 with a 0, 350 for that. And again, that's a larger estimate than this line. So this is smaller than this one. And that finally comes to, well, when I add these together, I get 478. So there's an estimate for calculation A, and it's bigger than calculation A. Let's do the same for B. The cube root of, well, that's pretty close to 1 million. So let's have a look at the cube root of 1 million. Now, 1 million we can think of as 100 times 100 times 100. That's a 1. Count the zeros, 6 zeros. So the cube root of 1 million, remember we're looking for a number, times itself 3 times gives me 1 million. Well, we're looking at it, it's 100. 100 times 100 times 100. 100 cubed is 1 million. So the cube root of 1 million is 100. So this is approximately 5 times 100. And remember, we reduced this 1,350,000 to 1 million. So we've got a smaller estimate than our original one. So the original one is greater than this estimate of 500. And looking at these two estimates, you can see that 478 is less than 500. So if we were to put these on a number line, 478 would be there, 500 would be there, and because 478 is bigger than the original calculation will be in there somewhere. And since 500 is smaller than the original calculation will be there somewhere. So it's definitely the fact that A is less than B. Calculation A is less than calculation B. So what have we got here? We've got question 16, and we've got a table of information regarding a swimming club members and a cycling club members. And we're told information about their median age, that's a type of average, and the interquartile range of the ages. And we have to compare the average age and the consistency of the ages. So let's look first of all at the median age. Now, I said the median age. Median is a type of average. There are several types of average. The median is the one where you put all their ages in order from the youngest to the oldest and choose the middle one. That's what the median is. And we're told in swimming club it's 21.2 and a cycling club is 29.7. So we could say that the average age in the swimming club is less than that in the cycling club. So the average age in swimming club is less, or younger than in the cycling club. So that's a comparison of the two numbers. Now the second one is consistency. Now interquartile range, if we do have all these data, all the ages, and we've got them in order, youngest to oldest, and we pick the middle one, which we said was the median, and if we pick the middle one of the bottom half, that's the lower quartile, or Q1, and the middle value in the upper half would be Q3. Now the quartile range is the difference between these two. So it measures how far spread out the ages are. And in this case, the swimming club ages are a lot more spread out than the cycling club ages. There's maybe a whole bunch of children and older people that go to the swimming club. Compared to cycling club, they're more consistent in their ages. Young, active people, maybe not so young and certainly not so old. So the consistency is more for the cycling club. So there is more consistency in the ages for the cycling club. So the first one, the average in the swimming club was less. Why was that? Because 21.2 was less than 29.7. And in our second statement, there's more consistency in the ages for the cycling club because 4.6 was less than 7.3. So if the interquartile range is less, there's more consistency. If it's bigger, they're less consistent, they're more spread out. Well, here we have question 17. And we're given a formula, y equals 3x plus 7 divided by x. And y is the subject of that formula. On the right-hand side, if we knew a value of x, for instance, suppose x equals 1, we'd get 3 times 1 plus 7 divided by 1. Well, that comes to 10. So if we know a value of x, we can find the value of y. If we are asked to change the subject of this formula to x, we want eventually to find something where we can put a value of y in, for instance y equals 10, and this time out would pop a value of 1 for x. So on the right hand side we want nothing but the letters y and some numbers and so on, but we want x on its own on the left hand side. So that's our aim in doing this. So our first move, it's awkward having a fraction here, so because we're in an equation, we look at the thing we don't like, which is divide by x, and we do the opposite, and that would be multiplying by x. So if we do that on the right hand side, to keep the equation balanced, we must do that to the left hand side. So we would now get y times x on the left. We're multiplying this by x so that that x disappears, and we're just left with 3x plus 7. Now, you'll notice that x occurs in 2 places. We're wanting x to occur only on the left. We only want y on the right. So the next move would be to get this 3x away from the right hand side, and we'll do that by subtracting 3x. And if we do that on the right hand side, we do that on the left hand side. So we'll have yx minus 3x. That 3x disappears and we're left with 7. Now what's next? Well, if we have a look at this left hand side, we can see that there's a common factor of x in each of these terms. So that can come outside brackets. Now let's multiply this out to see if things are working. X times y, y times x, that's okay. Minus 3x, that's okay. So what do we do next? Well, what's multiplying x? Well, it's this y minus 3, and we don't want y on the left, we want y's to appear on the right. So instead of multiplying by y minus 3, let's get rid of that by dividing by y minus 3. That's the opposite of multiplying by y minus 3. And again, we'll do that to both sides of the equation. Keep the equation balanced at all times. So if we divide this by y minus 3, that disappears and we're left with x. On the right hand side, we've got 7 divided by y minus 3. Now we've achieved what we set out to achieve. We've got x on its own on the left, there's no x's on the right, we've just got y on the right. And remember this example I gave you, we should be able to now plug in y equals 10 to get our value for x. 7 over 10 minus 3 is 7. 7 divided by 7 is 1. So there's a double check on the fact that this does give you the correct formula where x is the subject. So we've gone from y being the subject to x being the subject. So here we have question 18, and we're shown a diagram of a circle which has centre O and it passes through this point 0, 6. Now that would mean the radius of this circle is 6, and we're asked to write down the equation of it. Well, before we do anything, let's have a little look at an animation. So here we've got the picture of that circle, and I've chosen a point on the circumference. It has coordinates 4, 4.47. Now you can see this shaded triangle, and it's a right-angled triangle. The x-coordinate of that point, 4, squared, plus the y-coordinate squared, will give you 6 squared. There's the radius of the circle being 6. So that's Pythagoras' theorem in this right-angled triangle. Choose a point on the circle, x squared plus y squared will give you 6 squared. It doesn't matter whether that circle's there or moves around a bit, it will always be true that the x coordinate squared plus the y coordinate squared will give you 6 squared. If we go into a different quadrant where the x coordinate here is negative, when you square that you'll get a positive value and the result will still be true. So no matter where that point is, whether the coordinates are positive or negative, the x squared plus y squared will always give you 6 squared. So that's what we mean by the equation of this circle. It's true for every single point on that circle. X squared plus y squared equals 6 squared. And not just true for circles with radius of 6. There's a circle with radius 5, and every single point in that circle, the x squared plus the y squared of the coordinates of the point on the circle will be equal to 5 squared. So there's the equation of that circle, and we can reduce the radius to 4. That circle is equation x squared plus y squared equals 4 squared. X squared plus y squared equals 3 squared, and so on. So let's go back up to the one we're looking at, and the one in the question. The equation of that circle is x squared plus y squared equals 36. X squared plus y squared equals 36. Oh, here's question 19, and we're looking at 3 numbers, and we're given various bits of information about them. B, we're told, is 7/4 of A, and C, we're told, is A increased by 150%. So let's see what we can do with that. We're told that B is equal to 7/4 of A. Now, of gets replaced by times. And when we're multiplying fractions together, A is on the top, and it's like A over 1. So we multiply the top 2 numbers, and we multiply the bottom 2 numbers. So we get 7A over 4 for B. Now, let's have a look at C. This is interesting because A increased by 150%. Now, just a wee talk about 150%. That's 150 over 100. And if we cancel by 50, we'll get 3 50s make up 150, 2 50s make up 100. So that's 1.5. So it's increased by 1.5. So we start out with A and add 1.5 times A. So we've got 2 halves of A plus 3 halves of A. That's your 100% of A, that's your 150% of A that you're increasing it by. And how many halves is that? Well, 2A plus 3A, 5A over 2. Another way of looking at it is it's 2.5 times A. If you're increasing A by 150%, by 1.5 times, that's the increase. You already need the original, so you'll be multiplying it by 2.5. So there's the 2 values, and we have to write C as a fraction of B. 2 as a fraction of 4 would be 1/2. So the C as a fraction of B, C goes on top, B goes underneath. So C as a fraction of B, we know that C is 5A over 2. We know that B is 7A over 4. Now, what do we do to this? Well, we are in a big double-decker fraction. Let's call it a double-decker fraction. We can multiply the bottom of this fraction by 4, provided we do exactly the same to the top of the fraction to keep it balanced. Now, what cancelling goes on? Let's just look at the bottom of the fraction. 4 into 4 goes 1. 4 into 4 goes 1. And on the bottom of that double-decker fraction, we've got a single decker. We've got 7a. Top of the fraction, 2 into 2 goes 1, 2 into 4 goes 2. Cancel between the bottom and the top of this fraction here. So what have we got? 1 on the bottom. 5a times 2 is 10a on the top. 10a over 1 is just 10a. Now what next? Well, there's still cancelling that we can do. We divide top and bottom by a. And they cancel out. 10 times 1 is 10. 7 times 1 is 7. So we're left with 10 over 7. You can write that, if you like, as 1 3/7. But 10 over 7 will gain you the marks. 4 marks. There's all we are working out. Well, here's question 20. And we're given this identity. Notice there's 3 lines there. So this expression is identical to this expression. And we have to work out the values of a, b and c. So let's see what the left-hand side of this identity gives us. It's 5 lots of x cubed. It's followed by an x squared term, a lots of x squared, b lots of x, and a constant term, c. Now the right-hand side of that identity is k x cubed. We've got 2 minus k lots of x squared. We've got a squared minus 1 lots of x. And then we've got a constant at the end, b over 2. Now because this is an identity, then we know the numbers of x cubed must be identical. So from this we can say k is equal to 5. We also know that the x squared terms are identical, so if we have a lots of x squared, that must be the same as 2 minus k. So a is the same as 2 minus k. But we know what k is. It's 5. So a is 2 minus 5. Well, that gives us negative 3. Remember, on the number line, if you're at 2 and you take away 5, you'll be at negative 3. So this is working out well. Let's move forward. B lots of x must be identical to a squared minus 1 lots of x. So b will be the same as a squared minus 1. Well, we've worked out what a is. It's negative 3. Now watch out for this. It's negative 3 times negative 3 minus 1. And negative 3 times negative 3 is positive 9. Take away 1 will be 8. Now watch out, do not write negative 3 squared. That's negative 9, not positive 9. So this is great. Let's get a different colour onto this. What can we do now? Let's do a pink. C is identical to b over 2. C is identical to b over 2. And what is b? It's 8. So that's 8 over 2, which is 4. So final answer. A we now know is negative 3. B we've calculated to be 8. And finally, the value of C, that was a half of B, that's 4. Well, here's question 21. And we're asked to prove algebraically that this decimal, repeating decimal, is equal to 56 over 55. Well, usually what we do in a case like this is we call the repeating decimal x, because as yet we don't know what it equals. We're trying to show that it equals 56 over 55. And what does this repeating decimal look like? Well, the 2 dots mean that that 1/8 pattern repeats indefinitely. So that goes all the way along, never ends. And usually the trick here is either to multiply by 10 or 100. What we're trying to do is to shift that repeating pattern along so that it matches the repeating pattern again. Now we do that by multiplying, in this case, by 100. These repeating digits, there's a 2-digit pattern, which would imply we should multiply by 100. And you'll see how that works in a wee minute. So let's take 100 times x. Now what multiplying by 100 does, there's 2 ways of thinking about this. We either move the decimal point 2 places to the right, or alternatively move all the digits 2 columns to the left. And when we do that, we'll get the number 101.818181 repeating. 101, and that's where the decimal now goes. 81, 81, 81, and so on. Now, worth comparing that with x itself, which was 1.01818. And just as predicted, that repeating pattern now matches up. And the reason this is helpful is we now do a subtraction. So let's see what happens when we subtract these two. So we have 100x, and we take away 1x, we'll get 99x. There's 101, and we subtract 1, we'll get 100. There's the decimal point. Let's look at the tenths column. No tenths from 8 tenths gives us 8 tenths. Hundredths column, 100th from 100th, that's 0. 8 thousandths from 8 thousandths, 0. In fact, we'll get 0 all the way along to the right of that 8. What do we do now? Well, we're in an equation. We've got 99 times x, so we divide both sides by 99 to get 1x. Remember, in equations, we do the same to both sides to keep it balanced. So 99x divided by 99 will give us 1x. 100.8 divided by 99. Now, we don't like having decimal points in fractions like these. Let's multiply top and bottom by 10, and that'll give us 1008 over 990. Now it just remains to do some cancelling. Probably by the looks of this, 9 will divide into both of these numbers. So remember, there's no calculator, so we just have to slog this thing out. So 9 into 10 goes 1, 1 over. 9 into 10 goes 1, 1 over. 9 into 18 goes 2. So on the top of this fraction, we've got 112. And 990 divided by 9. 9 into 9 goes 1. 9 into 9 goes 1. And there's a 0 there. So we get 112 over 110. And because these are both even numbers, there's still a factor of 2 that can cancel. And so a half of 112 would be 56. And a half of 110 would be 55. So we've managed to prove that this repeating decimal is equal to 56/55. So here we have question 22, and we're given a diagram of a circle. We're told A, B and C lie on that circle. We're told the circle has centre O, and we're told that AP, this line here, is a tangent to that circle, and that BP, this line up here, is also a tangent to the circle. And we have to work out the size of this angle X. And we're told it's not drawn accurately, so we certainly aren't going to measure this with a protractor. We have to work this out using circle results. So let's look at a larger picture of that diagram. And one of the things that we know about a tangent to a circle is it touches the point of contact, in this case B, and if we were to join up this point of contact to the centre, then the radius and the tangent form a right angle. So let's do that. So there's a radius to the point of contact, and we're saying that that is a right angle. And there's also this other tangent. There's the point of contact A, and the radius to the centre will be at right angles to it. So let's draw that line in. And again, we have a right angle there. Now, the crucial part of this question is this angle here at the centre and this angle here out at the circumference. So let's have a look at a little animation showing this situation. So here we have a circle, and there's an angle at the centre of that circle. In this case it's 128 degrees, and coming from these two same points there's an angle at the circumference, and you can see in this particular case that that angle is 1/2 of this angle. Now that's true in general. It doesn't matter where that point is along this arc. That angle will always be 64 degrees, half of this angle at the centre. And if that angle at the centre changes size, so does the angle at the circumference, and it'll still be 1/2 the angle at the centre. There's an angle of 100. The angle at the circumference there is 50 degrees. A particular case is when the angle at the centre is a straight angle, 180 degrees. Then we've got an angle in a semicircle which is 1/2 of 180, that's 90 degrees. And that's another result that you should know. The angle in a semicircle is always 90 degrees. So that's a result that we're going to use in this question, that the angle at the circumference is 1/2 the angle at the centre, or the angle at the centre is twice the angle at the circumference, provided they're sitting on the same 2 points there. So what does that mean in the original question? Well, there's the angle at the circumference. There's the angle at the centre. This must be twice x. So let's look at the shape PBOA. Now that's a quadrilateral, so the four angles add up to 360 degrees. So let's write that down. So in quadrilateral, well, let's call it AOBP, the angle sum is 360 degrees. So let's write that down. We've got 2x plus a couple of 90-degree angles, that's 180 degrees, plus this 24 gives us 360. So 2x plus, now 180 plus 20 would be 200, and that 4, 204. And then to get 2x on its own, I'll take away 204 from both sides of this equation. That'll leave me with 2x, and 204, 200 from 300 is 100, 4 from 60 is 56. And finally, to get x, I'll half both sides. Half of 2x is 1x, a half of 150 is 75, and a half of the 6 is 3, so that'll be 78. So x is 78. So the size of this angle is 78 degrees. Well, here's question 23a, and we're given the first three terms of a geometric progression, and we have to work out the next term. Now, sequences of numbers that you've met so far, linear sequences, you start with a number, and to get the next term, you add the same amount each time. So if I'm adding d to a, I'll get a plus d. I add d again, I'll get a plus 2d. And so it goes on. Every time I add the same amount. So that's a linear sequence, sometimes called an arithmetic sequence or arithmetic progression. In a geometric progression or geometric sequence, instead of adding the same amount each time, we multiply by the same amount each time. So if we multiply the first term a by r, we get a times r. And we do the same process all the way along the line. That would be a r times r squared, and so on. So that's what a geometric sequence is. So in this case, we're given root 5 over 2, and to get to the next term, we're multiplying by something, and we don't know what that is. And we end up with 5 over 4. And then we're multiplying by the same number again to get 5 root 5 over 8. Now, how do we find out what this number is? Well, let's look at the first term, root 5 over 2. And we're multiplying by something to give us 5 over 4. Well, because these are fractions, let's pretend this one also is a fraction. So let's look at the top numbers of the fractions. Root 5 times something gives me 5. Well, root 5 times root 5 gives you 5. That's what the definition of the square root of 5 is. It's a number times itself gives me the 5. And 2 times what gives me 4? 2 2s are 4. So it looks like the number is root 5 over 2. Now, just to check that, let's take 5 over 4 and multiply it by root 5 over 2. What does that give us? 5 times root 5 over 4 times 2. And that is what the third term is. So it seems we're on to a winner with this multiplying by root 5 over 2. So this is the term that they're after, the next term in this sequence. So all we need to do now is multiply 5 root 5 over 8 by root 5 over 2. So let's multiply the top numbers. We've already got a 5 times a root 5. We've now to multiply that by a root 5. Well, we know root 5 times root 5 is 5 times this 5 at the front. 5 5s are 25. So on the top of the fraction we'll have a 25. The bottom of the fraction, 8 times 2, 16. So the next term in the sequence is 25 over 16. Now let's have a look at part B. And here we're asked to find the third term of a sequence where the nth term is 2 plus root 3 to the power n. Now to find the third term, we'll let n be 3. So we're looking at 2 plus root 3 to the power 3. And what does that mean? It means 3 of these expressions all multiplied together. Well, let's do it in stages. We'll leave this 2 plus root 3 at the front, and let's multiply 2 plus root 3 times 2 plus root 3. Now there's all sorts of ways you might have been taught about how to set out a multiplication like this. A lot of people put them into a table and multiply the corresponding terms. 2 times 2 is 4. 2 times root 3. Then here goes root 3 times 2. That's the same. 2 times root 3. And then root 3 times root 3. That gives us 3. And let's add up all these terms together. A 4 and a 3. That gives us 7. 2 lots of root 3 plus another 2 lots of root 3. That'll give us 4 lots of root 3. So in here, 7 plus 4 root 3. And let's now do the same for these two brackets. Let's set that out in a table. Let's do it over here. So we've got 2 plus root 3, and we're multiplying this time by 7 plus 4 root 3. Now there's no worries about negative signs in this. They're all positive. So 7 times 2, 14. 7 times that root 3, 7 lots of root 3. 4 times root 3 times 2. 2 lots of 4 root 3 will be 8 lots of root 3. And then 4 times root 3 times root 3. Well, we know the root 3 times the root 3 will give us 3. So 4 times 3 is 12. So let's add up. 14 plus that 12 will be 26. 8 lots of root 3 plus 7 lots of root 3 will be 15 lots of root 3. So there's our third term in this sequence. It's 26 plus 15 lots of root 3. So that's what we were asked to show. So here we have question 24, and we're told that 9k plus 7 and 2k squared plus 3 are consecutive integers, with the first one being smaller than the second one. And we have to work out what the next consecutive integer is. Well, what are consecutive integers? Well, 4 and 5 are consecutive integers, 10 and 11 are consecutive integers, and 9k plus 7 and 2k squared plus 3 are supposed to be consecutive integers. So what can we say about 4 and 5? Well, we can say that we get 5 from 4 by adding 1. And what can we say about 10 and 11? Well, we can get 11 from the 10 by adding 1. And what can we say about these two consecutive integers? Well, 2k squared plus 3 we can get from 9k plus 7 by adding 1. So I'm just following here the pattern that I followed in the previous two numerical examples. 5 is 1 more than 4, 11 is 1 more than 10, 2k squared plus 3 is 1 more than 9k plus 7. So that's what I've written down here. Now, it looks very much like we've got a quadratic equation here. 2k squared plus 3 is equal to 9k plus 8. 7 plus 1 is 8. And we know in quadratic equations we try and get everything onto the left-hand side equals 0. Remember, the strategy is to get everything on the left equals 0. We then try and factorize. So we get two numbers multiplied together gives you 0. So this one equals 0, or this one equals 0. And these are simpler equations that we can find the solution to easily. So that's the strategy we're trying to work out. So everything goes on to the left. So we get rid of 9k from both sides. And we get rid of that 8. And we do that to both sides. So we've got our 2k squared. We're taking away 9k. We've got 3. We take away 8. We'll have negative 5. We've taken away that 9k. We've taken away that 8. So we're sitting looking at 2k squared minus 9k minus 5 equals 0. And we're trying to factorize this quadratic, hoping to get two factors multiplied give you 0, so one or other of them is 0. Now, you'll have been taught different ways of how to factorize this. There's basically two ways. There's the FOIL method or there's the table method. It all depends how you multiply out these. The FOIL method, the firsts multiplied, the outside 2 multiplied, the inside 2 multiplied, and the last two terms multiplied. That's the FOIL method. And we look at the first term in each bracket. Product is supposed to be 2k squared. So we would have a 2k times a k. And then in the last product, we're trying to get a 5. Let's forget about negatives just now. 5 times 1 or 1 times 5. So I'm going to try 1 times 5. If this doesn't work, we would swap it round and try 5 times 1. Now the crucial bit is this outside product, 5 times 2k, that gives us 10k, and the inside product, 1 times k. And the question is, how from these two can we get the negative 9k? Well, we can do it by taking away 10k and then adding 1k. So it's the 10k that's negative, negative 5 times the 2k, and it's the 1k that's positive. Now when we multiply this out, you can check, we will get 2k squared minus 9k minus 5. So that's it factorised. Now the other way of doing that is again to say, okay, well, we have a little table of 4 terms and we're trying to get 2k squared. That would be 2k and k, and we're also trying to get the 5 times 1, forget about positives and negatives, multiply the whole thing, 2k squared, 1 times that k, 5 times the 2k, and then 5 times the 1. And there's your inside and outside pair, the 10k and the k. And to get negative 9k, this term would be negative, this one positive. And to get this negative, there's negative 5 times the 2k gives you negative 10k. And negative 5 times 1, that will give us a negative 5. So we've got a 2k squared, negative 10k plus k is negative 9k, and then there's a minus 5. So whichever way you do that, FOIL method or table method, there is this quadratic expression factorised. So we're at this stage, 2 factors multiply together to 0, one or other of these is as a 0. So either 2k plus 1 is 0, or k minus 5 is equal to 0. Now let's take the first one first. Let's take 1 from both sides. We get 2k equals negative 1, and then divide both sides by 2. We'll get k being negative a half. Now these numbers up here are supposed to be integers. 9k plus 7 is an integer. So if we replace k by negative a half, that is not an integer. You end up getting a fraction in there. So k does not equal negative a half. That's not a valid solution because that would give us not an integer up here. Now if k minus 5 equals 0, then k equals 5. And let's move on from that. 9k plus 7 would give us 9 times 5 plus 7. That's 45 plus 7. That gives us 52. Let's look at 2k squared plus 3. 2k squared plus 3. That gives us 2 times 5 squared plus 3. 2 lots of 25. That's 50 plus 3, 53. And we do get 2 consecutive integers. The next one would be 54. So the answer here is 54. Work out the value of the next consecutive integer, and that's it. So let's now look at part B, and we're told that x is a square number, and we have to show that the next square number is given by that. Now, square numbers mean you can take something and square it. Now, if we're trying to get x, then let's take the square root of x and square it. That gives us a square number. Now, the next square number up would be the square root of x plus 1 squared. I mean, suppose our square number was 144. That's 12 squared. That's the square root of 144 squared. The next number up would be 12 plus 1 squared. Well, that's the square root of 144 plus 1. So this is the next square number. We really need to work out what root x plus 1 times root x plus 1 gives us. And again, two methods. First, outsides, insides, last. Root x times root x would give us x. The outside product is root x times 1. The inside product, 1 times root x. And the last terms give us 1 times 1. And that certainly gives us x plus 2 lots of root x plus 1, which is what we were asked to show. And if you're doing it with the little table, then you've got root x and 1, root x and 1. And you fill in the various products. Root x times root x is x. Root x times 1 is root x. 1 times root x is root x. 1 times 1 is 1. And then again, you've got your x plus a couple of root x's plus 1, same as we had before. So that's part B solved. So, finally, we have question 25, and we're asked to show that the value of this trig expression is an integer. Now, if we look at what's in here, there's a sine 30, a cos 30, a tan 30, all in degrees. So, no calculator, how do we work out the value of sine 30, the value of cos 30, and the value of tan 30? Well, one of the ways we can remember this is to look at an equilateral triangle. Now remember, in an equilateral triangle, all sides are the same length. All angles are 60 degrees. And we chop it in half. So we have a 60-degree angle there, and we've chopped a 60-degree angle in half at the top. So we'll have a 30-degree angle there. Now, looking at side lengths, we'll choose any length for the 3 sides, but I'm going to choose 2 so that I don't get fractions. When you chop a side of 2, you get a length of 1. So all the other sides, this is 2, this is 2, and this is 2 halved. That's a 1. Now, Pythagoras' theorem would tell you that this third side in a right-angled triangle would be the square root of the hypotenuse 2 squared minus one of the smaller sides squared. 2 squared minus 1 squared. 4 minus 1 is 3. So this third side of this triangle is root 3. And from this, using SOHCAHTOA, or on your formula sheet, there is a diagram with A, B's and C's which you can work from if you want, but I use SOHCAHTOA. We're looking at the sine of 30. Sine is opposite over hypotenuse, so we're sitting up at this corner looking right across the triangle at the opposite side. That's 1. divided by, there's the hypotenuse, 2. So sine of 30 is 1/2. And what's the cosine of 30 degrees? Adjacent over hypotenuse. Sitting up at 30, adjacent is the side that's right next to you that is not the hypotenuse. So the adjacent is √3, the hypotenuse is 2. So it's √3 divided by 2. And the final trig expression we've got is the tan 30, TOA. The tan of 30, we're up at the top here, is the opposite divided by the adjacent. So that's 1 over √3. So that's what are called the exact values. Now some people just learn them. I usually write this diagram down and work them out. So we can now go to our expression, which is 6 lots of sine 30 plus 2 lots of cos 30 times 4 lots of tan 30. And we can plug in these values that we've worked out. So we know that sine 30 is exactly 1/2, so that would be 6 lots of 1/2 plus 2 lots of cos 30. Cos 30, the exact value is √3 over 2 times 4 lots of tan 30. Tan 30 degrees, exact value 1 over √3. So with 2 terms added together. Now the first term, 6 times 1/2 of 6, that's 3. The second term has 4 numbers all multiplied together. And remember, we can do cancelling between top numbers and bottom numbers. Just think of this as 2 over 1, 4 over 1. So on the top, we can divide by 2 so long as we divide on the bottom by 2. So there's a cancelling of 2, factor 2. √3 into √3 goes 1, √3 into √3 goes 1. We've cancelled the 2 √3 factors, top and bottom. Not a lot left there. On the top, we've got 1 times 1 times 4 times 1. Well, that just gives us 4. And we have to divide it by 1 times 1 times 1 times 1. That's just 1. Well, 4 divided by 1 is just 4. So our final answer to this is 7. And the question said, show that that is an integer. Seven is an integer. So there's the question completed, and that's the end of the paper. So that's Mr. Corsi signing out, and I hope you enjoyed the video.